Hi, welcome to Modern Optimization Methods. Today we will introduce the second part of Chapter 6, Semi-smooth Newton's method. Now let's first recall the definition for semi-smoothness. As we introduced in the previous part of this chapter, semi-smoothness needs to satisfy two conditions. The first one is that we require this vector function phi to be directly differentiable, and for any phi in the generalized Jacobian of phi at x plus h, the following equation to be satisfied. Furthermore, if a condition here, meaning that the left-hand side can be represented at the same order of the 1 plus gamma norm of h, then we also said phi is gamma order semi-smooth. Now, let's present the semi-smooth Newton's method. Actually, let's make a brief review about semi-smooth Newton's method. As we mentioned before, the semi-smoothness definition was originally proposed by Mifflin in 1977. Then it was extended to Newton's method by Qi and Sun in 1993. After that, it was widely used for vector problems. And now, the first extension to matrix problem is proposed by Qi and Sun in 2006 for nearest correlation matrix. After that, semi-smooth Newton's method received great attention from optimization community, and until currently, they acted as efficient subsolver for quadratic semi-definite programming problem and also for nonlinear programming problems. Now, let's take a look at the non-smooth version of Newton's method. Actually, we consider solving a nonlinear equation instead of solving optimization problem, okay? So we got this phi as we defined before from m-dimensional space to n-dimensional space. And phi x equals 0 is the system we are trying to solve. So the classical Newton's method to solve the system will update xk like this. So in each iteration, the next iteration xk plus 1 will be generated by xk minus the Newton's method. Okay? So Newton's direction is generated by vk inverse multiplied by phi at xk. Here, vk is the Jacobian of phi at xk. Okay? So in this case, Newton's method is actually assumed that phi is differentiable. However, for non-smooth Newton's method, it does not need the continuously differentiable of phi. We only assume that phi is a locally elliptic function and phi satisfies some non-smooth properties, okay? So in this case, we get the non-smooth Newton's method, meaning that when we update the Newton's direction, we choose this matrix Vk from the Clark's generalized Jacobian set. Okay? So the partial phi xk is what we have defined in the previous chapter. It is the Clark's generalized Jacobian, which is normally a set. Okay? So this is the non-smooth Newton's method. In other words, if at this point xk phi is differentiable, then this Vk is a unique matrix because you got the generalized Jacobian matrix coincides with the Jacobian set, okay? However, if at xk, this xk is not differentiable, so we need to choose the Vk from a set, okay? So any elements in this set is okay for this update, all right? So this is the definition for non-smooth Newton's method. And the relation between the two is that when phi is differentiable, then the non-smooth version will reduce it to the classical Newton's method. Otherwise, they are different. Now, let's take a look at the local convergence rate of non-smooth version of Newton's method. We assume that the generalized Jacobian set is non-singular and x0 is sufficiently close to x bar, where this x bar is the solution of the nonlinear system, okay? And if phi is semi-smooth at x bar, then we can analyze the local convergence rate in the following way. So we do the reformulation of the distance from the next iteration to x bar, okay? So this term we reformulate in the following sense, where we put out a VK inverse here, right? Then the inside of this part is represented like this. Here we add a zero term, phi x bar, okay? So notice that phi x bar is 0, right? Then this term, if we take a further look at it, then we can see that by our assumption, this inverse of VK is bounded, okay? And also we use the semi-smoothness property for the second term here, and we can see that this term is a high order of the distance of xk to x star. In other words, from the next iteration to the current iteration, if we take the ratio and taking limit, we can see that by the definition, the convergence rate is superlinear. All right, because you got high order relationship of the two terms here. And furthermore, if phi is gamma order semi-smoothness, then the high order can be reduced to the same order of the distance of xk to x bar. The order is 1 plus gamma, okay? So recall the strongly semi-smoothness, which corresponds to gamma equals 1, then we can see that if phi is strongly semi-smooth, then the order here will be 2. In other words, the convergence rate will be quadratic convergence. Okay? So this is a beautiful result. Now, we have finished the local convergence analysis, and we make a bit summarize, is that if we try to get the local convergence result, we need two essential conditions. The first one is that the semi-smoothness or strongly semi-smoothness of the function phi. Another condition is that we need the non-singularity of all the matrix V in the generalized Jacobian set. Why we need all the matrix V to be non-singular? Because in non-smooth Newton's update, we pick up any V, okay? So you cannot specify which V you choose. So we have to assume that all matrix V in generalized Jacobian set is non-singular. So with the two conditions, then we can guarantee the superlinear or quadratic convergence rate. Now, let's take a look at the global convergence result for semi-smooth Newton's method. And we consider solving the minimization problem. Okay, we try to minimize function f, which assume that function f is continuously differentiable. So it is equivalent to solving the gradient to be 0. Then we can see that the gradient to be 0 is actually the nonlinear equations that we are going to solve for Newton's method or semi-smooth Newton's method, okay? So we apply semi-smooth Newton's method directly to solve these first-order optimality conditions. And this is the update, okay? So we assume that a gradient f is semi-smooth and also the generalized Jacobian set is non-singular, then the local convergence can be guaranteed. So how we can get global convergence, okay? So to reach global convergence, as we recall in chapter 2 and 3, we need some step length in line search way, okay? So we add the following update like this. So we update the next iteration by choosing the semi-smooth Newton's direction. Then we use a line search alpha k, okay? So how do we do the line search? Next, we present a globalized version of semi-smooth Newton's method using the backtracking line search strategy, okay? Now, the algorithms are presented here where we replaced the variable x by omega actually, okay? So the settings is that we choose starting point omega 0 from any point, and we have some parameter sigma between 0 and 1, a ratio rho between 0 and 1, and delta eta 0 and eta 1, okay? So the first step is that we check whether we need to stop. If the norm of function f is small enough, we can regard that we have reached the optimality condition and we stop. Otherwise, we update and we go to the second step. The second step is that we choose any element from the generalized Jacobian set, and we solve the Newton's direction by conjugate gradient method, okay? So that's why we introduce conjugate gradient method in chapter 5. It is very important to apply CG to solve this linear system. In other words, we do not have to solve the inverse, okay, to solve the exact Newton direction. We just solve the inexact direction, okay? Until what? So this is the stopping criterion for solving linear system. And this actually means that we just solve the residue of the linear system, which can be bounded by a constant of norm of function f at the current iteration, okay? By doing this, we can already show the global convergence. And the third one is the step length that we apply. We apply the backtracking strategy to do the step length. That means that we start with mk equals 0 and increase mk 1 by 1 until we can find the following condition holds. Then we reach the alpha k in the form of rho power mk. After that, then we can get the next iteration in the following form, and the cycle go on and on. So by extending the non-smooth Newton's method to its globalized version, then it can be successfully used to solve other unconstrained optimization problems, and we do not have to worry about how to choose the initial point. Okay, so this is a very typical version for globalized semi-smooth Newton's method. Now, for the global convergence result, after adding the step length strategy, then we can guarantee the global convergence for the previous globalized version of semi-smooth Newton's method. Now, to make a brief summary, our previous presented globalized version of semi-smooth Newton's method will both maintain the global convergence result and fast local convergence result. Okay, so it is a very good algorithm. Now, let's make a brief summary about this part. We have introduced the non-smooth version of Newton's method and discussed the local convergence rate as well as the globalized version of Newton's method. We stop here and see you next time.